This video will cover the addition of organometallic reagents to epoxides. Epoxides are more reactive than the typical ether because of ring strain, and therefore will react with organometallic reagents. Let's look at an example. If we react a Grignard reagent with an epoxide, again in ether followed by the addition of water, we will get a primary alcohol as our product. The mechanism of this process starts with the Grignard reagent attacking the electrophilic carbon of the epoxide, causing opening of the epoxide. This produces the primary alkoxide ion, which then remains in this form until water is added. The addition of water protonates the primary alkoxide to give us the primary alcohol product. The epoxide we used in this example was symmetrical. What happens if we use an asymmetrical epoxide? When we use an asymmetrical epoxide, we need to consider the regiochemistry of addition of an organometallic reagent to the epoxide. If we add an organolithium reagent to this asymmetrical epoxide in the presence of ether followed by addition of water, we get only a single product, which results from attack of the organometallic reagent on the less hindered side of the epoxide. Following addition of water, the alkoxide ion is protonated to give us just the alcohol shown. It makes sense that the organometallic reagent would attack the less hindered side of the epoxide because it's easier for it to attack this carbon because there's less carbon surrounding it. However, remember that this is exactly the opposite of the regiochemistry of addition that we saw when we looked at acid-catalyzed opening of epoxides. The reasoning for the regiochemistry in acid-catalyzed opening of epoxides has to do with the stability of the carbocation. For example, if we take the same epoxide we looked at in the previous example and treat it with strong acid in the presence of a nucleophile, we again only get a single product, which results from attack of the nucleophile on the more substituted carbon of the epoxide. This is because this mechanism goes through a positively charged intermediate. Remember that the first step of this mechanism is protonation of the epoxide. This protonated epoxide has a positive charge on oxygen, but has additional resonance structures that place positive charges on either of the carbons attached to that oxygen. That means that there's a larger partial positive charge on the more substituted carbon attached to the oxygen. Therefore, the nucleophile attacks the more substituted carbon. This accounts for the regiochemistry of addition that we see under acid-catalyzed conditions. The final step is deprotonation to form the ether. This difference in regiochemistry when the epoxide is opened under basic conditions, as in when an organometallic reagent is used, versus under acidic conditions, as we saw in the bottom example, illustrates why it's so important to understand the mechanisms when predicting the products of these reactions.